Hello, welcome back to this online series of classes. The topic of today's class is alkynes, one of the important topics of your syllabus of second semester of Dibrugarh University, as well as the IGNOU's BCHCT 131 or CHC 05 of the earlier course. Okay, now what are alkynes? We all know alkynes are some unsaturated hydrocarbons. In the earlier classes, we have learned what are saturated and unsaturated hydrocarbons. Alkynes fall into the unsaturated part. So it contains one triple bond. General formula is CnH2SN minus 2. Here you see the general formula is CnH2SN minus 2. For example, ethyne, propyne, these are the examples of simple alkyne. Now, the alkynes can be classified into two classes. If the triple bond is present at the terminal, then it may be termed as a terminal alkyne. Like here I have shown one example, butane. If the triple bond lies in between the molecule and not on the terminal, then that type of alkyne will be known as internal alkyne. The triple bond of the internal alkyne may fall just in the center of the molecule or somewhere in between the molecule. It is not necessary that it is a symmetrical alkyne. It may be asymmetrical as well. The only requirement for internal alkyne is to have the triple bond is in between anywhere in the molecule, not in the terminal. Okay. For example, here I have shown an example here, the but 2y. Regarding structure, alkyne is sp hybridized. If it is sp hybridized, then it contains two sp hybrid orbitals. Here you see the blue colored two. Every carbon has two blue colored sp hybrid orbitals. One of the sp hybrid orbitals is used by this carbon to overlap with the another sp hybrid orbitals of the adjacent neighboring carbon to have a cc sigma bond. The second sp hybrid orbital, this one, it overlaps with the hydrogen atom to form a ch sigma bond. Ultimately, two sigma bonds are formed by every carbon atom. Every carbon atom is sp hybridized. If it is sp hybridized, then each carbon atom possesses two unutilized p atomic orbitals. One is this, another is this. These two p orbitals are lying perpendicular to each other. That is, if one p orbital is present in y-axis, then the other one is present in the z-axis. So this p orbital lying on one plane will overlap with the p orbital of the corresponding and neighboring carbon atom lying in the same plane. So one pi orbital is pi bond is formed. Similarly, the other p orbital also overlaps to get you back the second pi bond. So ultimately, we have seen here one sigma bond and two pi bonds are formed in by sp hybridization. If it is sp hybridization, the bone angle is, regarding hybridization, I hope you all know the shape is linear and the bone angle is 180 degree, a perfectly linear molecule. Okay. Another impact of sp hybridization is here you can see if we go from ethane to ethene to ethyne, from alkane to alkyne, the cc sigma bond has the bond length is 1.54 Armstrong, whereas cc double bond has 1.33 Armstrong and cc triple bond has 1.20 Armstrong. That means we have uh, seen here that the carbon-carbon bond length becomes shorter and shorter when we move from sp3 to sp2 to sp hybridization. So this is the effect of hybridization, which makes them shorter and shorter as we move from sp3 to sp hybridization. So ethyne has the shorter cc bond. Similarly, the effect of this also reflected in CH bonds also. in alkanes the CH bonds are also found to be 4.09. Here it is 1.09. Here it is 1.08 and here it is 1.06. The effect of hybridization also is reflected here in the case of CH bond lengths also. Now, isomerism in alkynes. Actually, there are two types of structural isomerism shown by alkynes. One is chain isomerism and another is position isomerism. In the chain isomerism, we have seen here that it is pent-1,1 and it is 3-methyl-1-butane. Both have the same formula, but the structural difference is seen here. One is straight, this one is straight, and here the hydrocarbon part becomes branched. So this type of isomerism is known as chain isomerism. In the position isomerism, we see that the position of the triple bond is different in the different molecules. Here the position of the both are pentane, but here the position of the triple bond is 1 and here the position of the triple bond is 2. That's why it is known as pent 1 1 and this one is known as pent 2 1. So this type of isomerism is known as position isomerism, where the position of the double or triple bond is different but the molecular formula remains same. Coming to the physical properties, first one is physical state and smell. The alkynes are somewhat polar as compared to alkenes and alkanes, because in alkynes the carbon atoms are sp heavy. So therefore more interaction among themselves are expected, and also the lower members of the alkynes are found to be gases because interaction is less, because less surface area is available. If the number of carbon atoms goes bigger and bigger, chain becomes higher and higher, and therefore the alkynes having carbon atoms more than 8 atoms are found to be liquid, and more than 8 are even found to be solid because the molecular interactions are greater, because the surface area becomes higher as the molecular weight is becoming higher and higher. Regarding color, alkynes are found to be colorless. However, ethane has characteristic color like garlic. You know the smell of garlic, it smells like garlic. Solubility, it's like alkanes and alkenes, alkynes are still insoluble because they are hydrocarbon like. They are, although they are weakly polar in nature, found to be less soluble in water, but they are lighter than water. So alkyne hydrocarbons also floats in water as they are lighter. However, regarding solubility, alkynes are found to be soluble in organic solvents like petroleum ether, carbon tetrachloride, benzene, etc. The most important physical property, as we have already discussed, is melting and boiling points. Here in the table you can see the melting point is ethane for ethane 101, for ethene 104, for ethine 191. That means the boiling point is becoming higher in the case of alkyne. So why this is so? Actually, we know that alkynes are linear in structure as it is sp hybridized. So as the molecules are linear, more surface areas are available for interaction with the similar type of other alkyne molecules. So more and more molecules can be associated with each other via more interactions in their linear surfaces. Moreover, as alkynes are more polar than alkenes and alkanes, so some polar interactions may also be expected. That this type of strong interaction actually makes alkynes having more melting point than alkanes and alkenes. Similarly, boiling points is also found to be for alkynes are found to be higher than the alkenes or alkanes. It is interesting to note that terminal alkynes have lower boiling points than isomeric internal alkynes. Okay. Coming to the preparation of alkynes, there are two general methods by which alkynes can be prepared. One is of course the industrial method known as from calcium carbide, and another one is synthetic one, that is from vicinal dihalides. So first of all, let us see how alkynes can be prepared from calcium carbide. We all know that we have in the society we may heard about the thing that bananas are being ripened by using carbide. Actually, carbides do not ripe the fruits or bananas. Actually, carbides formula is CaCO2, calcium carbide. They are formed by heating calcium oxide and coke in the electric furnace. When we place this type of carbide CaCO2 in between the fruits, they become and if we make them to settle in the hotter conditions, then with the reaction of the moisture, this calcium carbide uh, gets converted into ethine. This is the reaction. Actually, calcium carbide on reaction with moisture in presence of heat gets converted into ethine. Actually, this is this alkyne which makes the fruits ripe, not the carbide, as we have heard in our society. Okay, so this is a industrial method by which ethine can be prepared. As calcium carbide on reaction with water in presence of heat give you ethine. This is the main method of preparation of ethine, industrial method. Coming to the second method, it is from vicinal dihalides. What is vicinal dihalide? Vicinal dihalides are the dihalides where the two halogens are present in the adjacent position. That is 1, 2 position. So, for example, this one is a vicinal dihalide. If we react with this vicinal dihalide with alcoholic potassium hydroxide, elimination reaction occurs to give you vinyl halides or alkynyl halides. These alkynyl halides on treatment with a strong base like sodamide gives you the alkyne. Actually, this is an elimination reaction. Two elimination steps occurs to give you the alkyne. I will show you the actual mechanism by which alkynes are formed from vicinal dihalides in the next slide. Here is the mechanism. First of all, the amide ion, the base coming from sodamide, it is a strong base. This will attack at the beta carbon hydrogen. It will act as a proton, so it will abstract this proton as ammonia, and this bond is rearranged to give you the double bond. So this is a E2 mechanism. As the base is a strong base, so it forces the elimination to be follow E2 mechanism. So via E2 mechanism, this bromoalkene is formed. After formation of the bromoalkene, again amide ion is a strong base, again attacks on the beta carbon hydrogen. Then again another E2 mechanism takes place to get bromide leave to get the alkyne. So this we are getting the alkyne via two. Here you can see two steps are being involved in the mechanism. Both the steps are involving the E2 mechanisms. Okay. Next, another method of preparation of alkynes is dehalogenation of tetrahalides. Tetrahalides are containing 4 bromine atoms on the adjacent 1, 2 carbon atoms. If we treat with zinc, then zinc bromide is a very stable inorganic molecule. This two zinc bromide molecules will be eliminated like this, and ultimately unsaturation will be created and a triple bond will be generated. So we will be getting the alkynes. So lastly, I want to give you a very important conversion. Actually, it may be asked in your exams also, how you can convert alkanes to alkynes. So what you will do, first convert treat alkanes with bromine to give the 2-bromoalkane. It is the most stable major product. I have shown in the earlier classes why it is the major product, not 1-bromopropane. It is 2-bromopropane. So after formation of the 2-bromopropane of the via halogenation of alkane, this is heated with the presence of alcoholic potassium hydroxide to get to cause the E2 elimination to get the alkene, and then this alkene is treated with halogenation with the help of bromine. Then we will be getting 1,2 dihalo alkane, that is vicinal dihalide. And we know how we can obtain alkynes from vicinal dihalide. This is the vicinal dihalide, again treat with sodamide, strong base, then you will get ultimately the alkyne. So you can convert easily alkanes to alkynes by this route. Lastly, I am giving some homeworks for you to practice over today's class. First of all, by writing appropriate chemical equations, how each of the following compounds can be converted into one hexane, from 1 to dibromohexane, from 1 hexene, and from hexane. How these can be converted to 1 hexane. So these are the answers. You can check it out. Direct treatment with sodamide. Second one, first treated bromine, then treated sodamide. Third method, first of all convert the alkane to bromoalkane, then treat with alcoholic potassium hydroxide, then halogenation, and then again elimination. You will get the alkyne. So I am giving this for your practice. Very important questions for your exam. So thank you very much for attending today's class, which is basically I have covered in this class the introduction part and physical properties and preparation of alkynes. So in the next class, another class I will do perform for alkynes. In that class we will be discussing about the chemical properties of the alkynes. Till then, bye bye.